Hi everyone. In this video we're going to practice reactions that involve ring opening of epoxides. So we're going to consider whether we have acidic conditions or basic conditions and whether we have a tertiary carbon or not. All right, so let's start by drawing an alkene. Okay, so there's our alkene, and we're going to add MCPBA, followed by a catalytic acid and methanol, which is an alcohol. Okay, so what I would like you to do is pause the video and see if you can figure out what the product would be for this reaction, or products if there's more than one. And then when you unpause, we'll go over it together. Okay, so in the first step, we're adding MCPBA, which is going to create an epoxide. And I'm actually going to abbreviate my benzene ring as PH, which stands for a phenyl group, which is really just a fancy word for a benzene ring. Okay, and that will make it a little bit easier. All right, so I've got my epoxide that formed across the double bond, and now I need to draw in my substituents. And I'm noticing that my two methyl groups are cis to each other. And then there's also a hydrogen on that carbon. And those, or the hydrogen and the phenyl group are cis to each other. So I'm just going to arbitrarily draw the methyl groups as wedges. You could also draw them as dashes. That's fine too. And then I'll draw my phenyl group as a dash and my hydrogen as a dash. Okay, now remember the epoxide could have formed below the plane of the double bond as well. So we are going to also form the enantiomer of this structure too. All right, so next we're adding catalytic acid as well as methanol. So remember, under acidic conditions, the oxygen in the epoxide is going to grab a hydrogen or deprotonate the acid. All right, and then once it's protonated, the nucleophile can come in and attack. So our nucleophile in this case is methanol. Now we have to figure out which carbon is methanol going to attack. The left-hand carbon or the right-hand carbon? So let's look at the left-hand carbon. Is that primary, secondary, or tertiary? Tertiary, because that carbon is bonded to 3 other carbons. And then what about the carbon on the right? Is that primary, secondary, or tertiary? It is secondary because that carbon is bonded to 2 other carbons. All right, so remember we are under acidic conditions and we have a tertiary carbon available. So our nucleophile will attack the tertiary carbon. So let's just draw that arrow coming in and then our ring will open up. So I just drew a lot of steps all at once. So remember, first we protonate the oxygen, and then second, the nucleophile attacks, and then third, the ring opens up. Well, the nucleophile attacking and the ring opening are kind of in the same step, but you get the idea. All right, so now we have our nucleophile bonding to the tertiary carbon, and then our alcohol group is opposite that. And then we're just going to draw in our wedges and dashes for each carbon. And remember, we also have the enantiomer for this structure as well. Okay, and then in the last step, we're just going to deprotonate that oxygen, probably using the methanol. And we get our final product. Or I should say products, since we have an enantiomer. Okay, so again, remember, under acidic conditions, if there is a tertiary carbon available, the nucleophile will attack that carbon. If there are no tertiary carbons, then the nucleophile attacks the least substituted carbon. Okay, let's do another problem. All right, so I'll draw another alkene here. And this time we'll treat this with MCPBA, followed by a phenyl group in a Grignard reagent. So remember, pH stands for a benzene ring, or phenyl group. And then third, we're going to add acid. Or actually, let's not add acid in this case. Let's add H2O, just to make it clear that we're not under acidic conditions. So these will be non-acidic conditions. Okay, so let's see if you can figure out what the products look like. So pause the video, try this on your own first, and then we'll go over it together. All right, so again, the first step, we're adding MCPBA to form the epoxide. And we have to figure out which of our substituents are wedges and which ones are dashes. So looking up above at our alkene, let's see, we have a methyl group, cis to an isopropyl group. And then we also have a hydrogen that's not shown, but that is cis to the ethyl group. Okay, so I'll just arbitrarily draw the ethyl group and the hydrogen as wedges, and then I'll show the methyl group and the isopropyl group as dashes. And here I'm abbreviating isopropyl as IPR. And remember, we're also forming the enantiomer of this structure because the epoxide could form below the plane of the double bond as well. All right, so then in our next step, we're adding our Grignard reagent. And I said that a phenyl group is in our Grignard reagent. So let's draw what that would look like. So we have a benzene ring with a negative charge. Okay, so again, we're under non-acidic conditions. We don't have any acid present. So where would that nucleophile attack? So where would the negatively charged benzene ring attack? The left side or the right side of the epoxide? The right-hand side, because if we characterize our carbons, the one on the left is a tertiary carbon, the one on the right is a secondary carbon. And remember, under non-acidic conditions, the nucleophile always attacks the less substituted carbon. Okay, so let's draw the phenyl group attacking that carbon. The ring opens up. All right, so now we have our phenyl group bonded to the secondary carbon, and we have a negatively charged oxygen on the tertiary carbon. And then I'm just going to draw in all of our other groups here. IPR, and then ethyl and methyl, plus the enantiomer. Okay, and then in the last step, we'll use water to protonate our negatively charged oxygen. And we get our final product. Plus the enantiomer, of course. So again, if you have non-acidic conditions or basic conditions, the nucleophile always attacks the less substituted carbon. Okay, so let's kind of focus now on synthesis. How can we use an epoxide to our advantage in a synthesis problem? So let's go over a challenge problem. Let's say we're starting with an alkyne, a terminal alkyne, and we're trying to turn this into the following. So we have a primary alcohol. All right, so this might involve some retrosynthetic analysis. We might have to go backwards to get to the starting material. But I will give you a hint. We will use an epoxide in this problem. All right, so see if you can try this on your own first. And then when you unpause the video, we'll go over it together. Okay, so probably the first thing I'm noticing here is the difference in the number of carbons between my starting material and my product. So if I count the carbons, I have 1, 2, 3, 4 carbons in my starting material, but I have 1, 2, 3, 4, 5, 6 carbons in my product. So at some point I'm going to add more carbons onto this structure. All right, so again, let's do some retrosynthetic analysis here. And if you are struggling with this problem, don't worry, this one is challenging. So one trick that we can use is if you notice that your alcohol is on a the least substituted carbon, that means that you could have added an epoxide in order to get that alcohol. So, in the step before we got our alcohol, we could have used an epoxide and a Grignard reagent. So remember from before, we talked about how with a Grignard reagent, adding to an epoxide, you could increase the length of your carbon chain. So here, the carbon in our Grignard reagent is negatively charged, and it can attack one of the carbons in our simple epoxide, and that will open the ring. But then we have to protonate that oxygen, so in step 2, we'll add some water to protonate it. Okay, so that will give us our 6 carbon chain. So we have 1, 2, 3, 4, 5, and 6. So again, this was a really challenging step to figure out, so don't feel bad if you didn't figure that out right away. Okay, so now we can work backwards and say, how do we make a Grignard reagent? So remember, we can use pure magnesium in some sort of ether as our solvent. And the ether solvent just stabilizes the magnesium ion as it forms. So that's why we use the ether there. And we also need an alkyl halide. So let's just use the same basic structure that we had. And we'll just put a bromine on the end there, because we do know that magnesium is going to squeeze itself in between the bromine and the carbon. Okay, so how can we make, let's see, this alkyl halide? Well, if we want, we could use an addition reaction across a double bond. Okay, so let's use our basic carbon structure here. And where would the double bond go? So it would have to be on the end, right, in order to add bromine on the end of the molecule. And what reagents would we use to add bromine to the end of the molecule? So we would use HBr, but in order for bromine to add to the less substituted carbon, we need to add peroxides. Okay, and then let's see, is there any way to go from our starting material, the alkyne, to our double bond, the alkene? Yeah, we have a couple different ways we could do that. We could use H2 and Lindlar's catalyst, or you could use sodium and ammonia. So remember, hydrogen with Lindlar's catalyst will give you the cis alkene, and then sodium and ammonia will give you the trans alkene. But in this case, the alkene's on the end of the molecule, so it doesn't really matter which one you use. All right, so again, the really key step here was that last step where we added the Grignard reagent to the epoxide. So again, if the alcohol in your product is on the least substituted carbon, you need an epoxide. Now, what if the alcohol was somewhere in the middle of our molecule? So if the alcohol is on a more substituted carbon, then you need a ketone or an aldehyde. And then you can turn it into an alcohol by using a reduction reagent. Okay, so I hope that helps with epoxides and synthesis problems and figuring out where a nucleophile adds. In the next video, we're going to wrap up chapter 13 and just talk a little bit about thiols and sulfides. But for the most part, this chapter was all about ethers and epoxides. So we're just going to briefly cover thiols and sulfides. So I will see you then.